Hi, and welcome to our discussion on atmospheric dynamics. We're going to continue our discussion on balanced flow, and specifically in this video we're going to look at the gradient wind, an introduction to the gradient wind. So we'll start out with our horizontal equation of motion. We've looked at this before when we looked at the geostrophic wind, and we made some assumptions. So we're going to take this equation again and start making some assumptions. The first assumption is that the flow is frictionless. So frictionless means that you're looking at winds that are in the upper atmosphere away from the surface layer or the boundary layer. The other thing that we're going to do is when we had geostrophic wind, we got rid of this acceleration term. But let's hold on to that now, and we'll look at the acceleration that results from curved flow. So you remember that geostrophic wind was straight, unaccelerated flow. Here we're going to look at wind that is not accelerating in magnitude. In other words, you're not going to see the wind speed increase, but if it's going around a curve, technically that's acceleration. Acceleration is anything or any time you have a change in velocity with time. And if we look at a couple of velocity vectors, we can see that after a period of time that the wind has gone around a curve. You're looking at velocity vector 1 moving over to position 2, v2. So there was a change in the velocity with time. In this case, it's not so much the magnitude or the speed of the wind, but it's the direction. The direction changed. So because the direction changed, there's an acceleration. So what we could do is vector addition or vector subtraction to figure out what the acceleration is. And by definition, acceleration is v2 minus v1 divided by the time. So here we're looking at v2 minus v1, the change in the velocity vector. Not so much the speed, but the direction. So if we make that difference or do that subtraction, we see that there is a vector that is pointing in towards the center of the curve, and that is your acceleration vector. So even though it's not changing magnitude, not changing speed, there is acceleration because of the change in direction. We call that acceleration centripetal acceleration, and centripetal means seeking the center. So as the wind goes around a turn, there is something that's causing it to turn, and we call that the centripetal acceleration. Just like an airplane, some of you have probably learned that the horizontal component of lift is what makes an airplane turn. Likewise, there's the centripetal acceleration that's making the wind turn. Now, as a result of the centripetal acceleration, there's a force or an acceleration in the opposite direction, trying to keep the air flowing straight and not curving, and that is called centrifugal acceleration. It's equal and opposite of the centripetal acceleration. So you can think of it as a car going around a turn. The tires are what keeps the car turning in the circle, but you feel an acceleration to the outside of the turn, and if you're not bolted into the car, you'll be pushed or thrown out of the car to the outside of the turn, and that is your centrifugal acceleration. So what determines centrifugal acceleration? Well, number one, the faster you go around a turn, the greater that acceleration towards the outside of the turn. So it's directly proportional to speed. And the acceleration, centripetal acceleration, is also inversely proportional to the radius of curvature, meaning that for a really big radius, a very gentle curve, you're not going to have great acceleration to the outside of the turn. But if it's a really sharp curve, really small radius, then you're going to have a greater acceleration to the outside. So it's directly proportional to the wind speed, or the speed of the wind, squared and inversely proportional to the radius of curvature. So bigger wind, faster wind, you're going to see more acceleration, and a smaller curve, you're going to see a greater acceleration also. So we're going to substitute that in for our acceleration term. And in this case, it's all resulting from the change in the direction of the wind. Not so much the speed is accelerating, but it's the direction that's changing, and that results in the acceleration. So here's our new equation. This is the equation for the gradient wind. It says the centrifugal acceleration is balanced by Coriolis and also pressure gradient. Now this is looking at a constant altitude chart where height is the vertical coordinate. Or in natural coordinates, you can replace the change in pressure in the x or y direction with a change in pressure in the n direction, n being normal to the flow. So this is on a constant altitude chart once again because we have pressure. You can also substitute the pressure gradient for the height gradient, and we've done that before in other balanced flows. So we'll continue on with the gradient wind in the next video.